So, welcome to a new lecture of probability statistics and Happy New Year from the three of you that are here, which is good. Thank you very much for being here very early in the morning on January the 10th. I couldn't say Merry Christmas or Happy New Year because I was not here in the last lecture, but today we will have in person. Next week I will have to travel again, so I will not be here, so I will post a video for you that don't come next week, but the week after we will continue with our regular in-person lectures. That's important announcement. Today we have lecture number 10. We have in total 13 plus one that I will teach you or show you how the exam will look like. So it might be very nice if you want to join in person, because I will not record that lecture. So for the one that comes, it's actually an advantage, let's say. But today we have bootstrapping, chi-square test, and student t-test. Okay, and we will go through what bootstrapping is and why we want to show it here. Then, if you remember from the last lecture, there is basically in statistics two different words. One is the parametric, the other is the non-parametric word. And one important, let's say, assumption using parametric test is to have normal distribution of the residuals from your model, right? And one way to test if your data follows a normal distribution is using, for example, the chi-square test, which uses a chi-square distribution. But chi-square distribution or chi-square test can be used to test if your data follow any distribution. So, but in particular, it might be interesting for you to know how to test if the data follow a normal distribution. And then we'll start the parametric world, let's say, today with the t-test, which is one of the most famous probability tests for comparison of means, and in particular the student t-test. And let's see how we describe the t-distribution, another distribution in these lectures, and how we can use this distribution to test difference between means. So, basically, bootstrapping is a way of resampling data. So when you have not enough data, sometimes you want to, in some way, get synthetic data that kind of follow the distribution that your population comes from. And it's not always advisable to create synthetic data, but sometimes it becomes really useful or important. For example, when you're using clinical data or study with animals, you cannot use experiments that use large amount of animals because of ethical reasons, or large amount of humans because of ethical reasons, until you get to have 8 subjects or 8 animals, and that is the power of the analysis reduced significantly. So we sometimes have to create more data, and at least that the data follows the trend that you want to study. So in this lecture, I just wanted to show that there is at least 2 ways of doing this. There is many methods to resample data, but one is the jackknife, which we're not going to cover here, and the other, 2 more famous, let's say. And the other is the bootstrapping, which we will cover today. And it has nothing to do with strapping your boot, but in some way it might be a good way of memorizing the word if you imagine a boot and a strap. So basically, bootstrapping then it works in the way that it's a distribution-free resampling of your data. So you don't assume any distribution, you just draw data repeatedly until you could do it many times, and then you estimate the mean and the variance every time you draw data from the same amount of data point that you have. And I will show you in a minute how you do that. and the idea is that if you randomly pick the same point many times, you can estimate better the mean and the variance of the whole population. It's like an imagine that you have more data that you actually have. So basically what you do is, I have two videos here that shows what it does, but let's say that we have 20 points. You only were able to collect 20 points. And these have, so you have the bottom point here and you have the box plot there. So you see that the median is around here, and then you have the lower and upper quartile. And the idea is that you have to draw exactly the amount of data that you already have. So if you have 20 points, you will have to draw randomly 20 points. When you pick randomly 20 points, you might pick some of the points 2 times because it's randomly, okay? So it's always replacing every time that you draw 1 point. And sometimes maybe you even don't draw one of the points, okay? But the idea is that you repeatedly draw 20 points and you calculate the mean and the standard deviation, or the median and the quartile, okay? So something like this. So, if that doesn't work. No, that's the thing. Okay, doesn't like it, this neither. Okay. That work if I play it like this? No. Okay. Well, so the idea is that basically you would draw it, and I can make it. Let's say that you have one run and you pick randomly this point, and then maybe you pick this point, and maybe you pick this point, and this point you pick it 2 times, and this point maybe 2 times, and so on and so forth. And then the distribution will move a little bit, maybe, right? And then you run again, and you pick another 20, and then maybe the distribution moves now a little bit here, right? And then you do it for, let's say, 200 times, and then combine this box plot. Let's say you take the mean of the median, the mean of the standard variation, and then you will have a final one that kind of follow your distribution, okay? So that's pretty much the idea. The video will show you much better, actually. So basically, let's say that you have 55 points that you have collected. And in one realization, you pick, this goes from 1 to 55, right? You have 55 points. The first one that you pick is a 9, the second is a 9, then an 8, and a 6, and so forth, right? So you pick 55 points randomly from here. Then you take the mean and the variance, or the standard deviation, okay? And then you have a value that is 9.89 and 1.4 for the variance, right? Then you run it again. Let's say that you run for a second time, and you pick the 6, the 9, the 6, the 10, and the 9. And then you will have a new set of mean and standard deviation, okay? And then you do it for many times until you get 250 times. And you will, in the number 250 times, you get another set of mean and variance. So the idea is that you order all your 250 variance and mean from the lowest to the highest, okay? And then you try to find a confidence interval where your true mean and variance will lie in, okay? So let's say that we want to have a confidence interval of 95%. So we want to be sure that we cover 95% of basically your point. So one confidence interval will be at 0.025 of your 250, and the other border will be at the upper 0.25 of your 250, okay? So if you multiply this, you will get that you should be in the lower part 6.25 and in the upper part on the 243.75. Since they are discrete, you have to choose the next one. So you cannot be a decimal point, you have to be in an integer, right? So it will be 7 and 244, okay? So if you do that, then you can come to your set of data and you count. 1, 2, 3, 4, 5, 6, 7. This is your border. And then 250, 49, 48, 47, 46, 45, 44 is your other border. Okay? And you do the same for the mean. Okay? And then you build your confidence interval. So you don't know the mean exactly, you don't know exactly the average, but you know that the variance would lie between 1 and 2 and between 8 and 11. It's the best that you can do with the data. But at least now you have a better estimation than just taking the 20 point and calculating the mean and the average and the standard deviation. Okay, it's a way to estimate this parameter with creating more synthetic data. And like I said, it's not always advisable, it can be biased, so you have to be very careful when you do this kind of thing. But it might be good, especially when you are, for example, testing algorithms. It might be a good way to test your algorithm with more data than what you have in real. Okay, so bootstrapping is something on the side for you to know that this exists. But let's focus on the main core of the next 2 or 3 lectures. Will be the non-parametric and the parametric world. Like I said, to choose for the parametric method, you have to know if your data follow a normal distribution. And one way to do that is using the chi-square distribution. And the chi-square is a distribution that comes from summing together and squaring variables that have a normal distribution. So if you have x1, 2, 3, 4, n variables that follow a normal distribution, you square them and you sum it together, you will get a chi-square distribution. So this new variable set or chi-square will follow a chi-square distribution. Okay? And believe me or not, this is the formula for the density function of the chi-square. It comes from, we saw that 2, 3, 4, 5, 6 weeks ago, from the gamma distribution. I don't know if you remember. First, remember that the gamma distribution is defined differently here in Europe than from the USA or the British. And the only difference is that alpha is staying the same, but beta is 1 over beta for some reason defined in the USA. But this is the formula for the density function of the gamma distribution. So if for the gamma distribution, particularly, you take alpha as n divided by 2 and beta as 1.5, the gamma distribution becomes the chi-square distribution. That's all. It's a particular case of the gamma distribution. N is not n the number of data, it's the degree of freedom. And we'll talk about this in a few minutes. Okay? Then this is your density function. You can make it easy if the constant part here, you call it A, and then it's easier for you to remember for way easy. It's less complicated. But when I say n, it's not the number of data, it's the degree of freedom. This comes to the naturals. The degree of freedom in any distribution is defined as the number of data that you have minus the parameters that you want to estimate from the distribution. And to say that, let's imagine you have this example. Let's say that you are here in Intec and you have a pool of 30 students that drink beer, right? And you want to see how the consumption of beer in a week or in a month is for the students. So you will have some people that drink a lot and you will have people that drink one or none, okay? And then maybe there's gonna be some distribution, right? Some people in some way will drink differently. So let's say that in average from this, you have 23 cans of beer drinking in average in a month, which less than a beer per day, which I think is already good enough. So from this average, it was constructed in some way, right? So it was, the average is always the sum of each of the students, the consumption of each student, divided by the number of students that you have, right? So you can say that the sum of this consumption is equal to the number of students times the average. That's the only way to say that, right? So for student number 1, it can pick anything. So it could be 5, right? For student number 2, also can be 30. Number 3, number 4, it can always be free to do whatever they want. Now when you get to student number 29, then there is only one option for that guy, because to be able to multiply n times the average to become the number that is here, okay? So student number 29 is not free to be any kind of consumption if you want to follow this formula. And this is the degree of freedom that you lose when you estimate the average of this distribution. Because 29 of the 30 students were able to be placed in any place, but the number 30, or the number 30, sorry, not the 29, the number 30 has to be placed in a position here such that n times the average is equal to the summation of all the consumption. Okay? Is that making sense in some way? So you lose 1 degree of freedom. So to estimate the average of the distribution, your degree of freedom would be 30 minus 1, 29. Okay? And you can generalize this as the degree of freedom will always be the number of points that you have, or the sample that you take, minus the parameters that you want to estimate. If you want to estimate the mean and the variance, then there is another formula, right? You have, so now you will lose 1 point because you have to estimate the mean, and then you will lose also 1 point because you have to estimate the variance. So that these two formulas can be met, correct? And then the degree of freedom will be 28 in this case. Okay, having said that about degree of freedom, which is important for distribution, there are some shortcuts that you can take when you calculate the famous gamma function, right? The gamma function, it was n minus 1 factorial. If for some reason n is equal to 1.5, you get the square root of pi. If the gamma function of 1 is 1, and so on and so forth. That's just for you to know if you need it for the exercises. How the chi-square distribution look like, as we show in every distribution. This is the CDF, and this is the this is the PDF, and this is the CDF. So for different values of for different degree of freedom, it looks in a different shape. Different degree of freedom also gives different cumulative distribution. The mean is equal to the degree of freedom and variance and standard deviation that define data. Just for you to know, just for completeness. So, as any distribution, you can calculate borders, right? As we do it, as always, that we test, that we do hypothesis testing, that we're going to use in a few minutes. Let's say that you have a variable that follows a chi-square distribution, and you have, for some reason, degree of freedom 10. So, and then you want to know what is the probability, or what is the carrying value, such that the probability will be less than 95%, right? So what you do, as any distribution that we have seen so far, there is a table, right? And this distribution are tabulated, so you will have all the probabilities and standardized given the degree of freedom that you have and given the cutting value that you are looking at, okay? And in this case, we want to use 95%, and we want to use degree of freedom 10. So that's going to be a table like this. And since we are looking at the interval that is less than A on the 95%, the table here is larger than A, so you have to look at the 0.05 instead of the 95%. And then you look for the 10 degree of freedom, and you get here 18.39, and this is what I have here. Just a briefly thing so you can see how we proceed next. But basically there is a distribution, as always. There is a cutting point where from the to the right you have less than 0.05, and to the right you have more than 0.05. So for what is good the chi-square distribution? So like I said, we can test if your data follows some distribution. It can be any distribution. You can also check it for population dependency, and so if two samples are independent, and for homogeneity. Homogeneity means, for example, if you remember the video of the dragons and the wings, if you watch the video, there was something like the wing span distribution was something like this. So this is not such a homogeneous distribution, so it looks more like a bimodal distribution. And then you can test if the distribution is homogeneous or not with the chi-square distribution. So how you test? As always, as we have seen before, we have to set up a hypothesis testing scenario where, for example, let's say that we want to go for this one, for test of population distribution. You want to know if your data, the distribution is equal to such a distribution F naught, okay? And the alternative is would be the null hypothesis. The alternative hypothesis is that it's not following that distribution, okay? So from that you can use the chi-square distribution to test this, and let's see how we do this. First, there are a few steps, right? Let's say that your data look like this. You have probability here, and you have your X here. And let's say that you have something like, I don't know, it could be anything, point like this, right? You have collected, and you have the frequency of appearance of this X over time. And then you have to set up, in some way, bins, okay? So you will have to construct arbitrarily, some way, bins that represent your data, okay? And this bin will have some height and some width. And the multiplication of the height and the width will give you the area, which is the probability of this bin to happen, okay? And you want to test this if it follows, for example, a normal distribution, which is the theoretical one. So basically, with the chi-square distribution, we will be seeing the difference between the height of this bin, or the area of this bin, and the area covered by the theoretical distribution, okay? If this difference is too large, then your distribution does not follow that particular distribution. If the difference is not too large, then you will follow, and you can actually say. And you will say with some confidence, 99%, 95%, as we always do. And the way that the difference between them would follow a chi-square distribution. Okay? So first you set up your bins. Then you have to calculate at the height of the bins what is the value of your theoretical distribution. And then you will have to subtract them and divide it by the width of the distribution. And this subtraction, the summation, will follow chi-square distribution. And depending on the value of these statistics, we will enter the table, and we will first set up a critical value, right, to see, I want to be sure at 95%, right, or with a 0.05%, 5% error, and then we will compare these two values to see if it actually is statistically different or not from this distribution. And how we do that? We have to build a table like this, and I know that this might be a little bit messy at the beginning, but you will see with an example much easier. First, you have to find your you have your beams, and then you have to find the height of this beam. This is something that you observe from your data, and this comes here. Then you will have to have your theoretical distribution, and then you will have to say, well, which one will be your theoretical value, and you put it here. And then you multiply the theoretical value by the width of this, and then you have your theoretical area, okay? Then you subtract the theoretical area from your observed data, and if you square it and divide it by the theoretical area, you sum it all together and you get your chi-square value here. I'll show you in a minute how you do that. And then with that you enter the table, but let me just skip it so you see the example how it looks like. Let's say that we have a die, okay, as always, right? If it's an honest die, we know that the distribution should be flat, right? At 1/6 for 1, 2, 3, 4, 5, 6, right? So we have 6 faces of the die. If you throw it, all of the faces with an honest die should have a 1/6 probability to happen, okay? So, let's say that we have a die and we don't know if it's an honest one, and we want to test if it follows a flat distribution or a uniform distribution. It should be actually an honest die. So we have a die and we throw it 120 times, okay? And from the 120 times that we have thrown the die, 15 times you get a 1, 19 times you get a 2, 22 times you get a 3, 21 you get a 4, 17 you get a 5, and 26 you get a 6. Okay? So from that, we will see how we can test it. So the first thing that we have to do, we have to build our classes. The classes are easy to build in this case because we have already defined it. It's 1, 2, 3, 4, 5, and 6. And then you have 15 for 1, 19 for 2, 22 for 3, 21 for 4, 17 for 5, and 26 for 6. And in reality, there should be a flat line here, right? So we're going to compare the non-uniform distribution to this set of pins. So we define the classes as 6, and we have the value for that. Second part is you define the probability, the theoretical one. We know that all should be 1/6. So the first column is already filled with our classes and the values inside the classes. Okay? This is what we have. The second column, for all of them, there should be 1/6. Okay? So 1/6 for the second column. The third column is the width times the probability. If we have 120 and it's a uniform distribution, the only way is that each of the beams has 20. Okay? So that is defined like that, and then we have to subtract 20 to 15, or the other way around. It doesn't matter because at the end you will square it. 20 from 19. 20 for 22, and so on and so forth, and you build the fourth column. Then at this subtraction, you have to square it and divide it by the theoretical area. And then you do that for each row. And the last one will be the sum of all of the rows. And this guy here is your chi-square statistic. With this chi-square statistic, you will compare this chi-square statistic with the critical value of the chi-square distribution, and if it's lower than that, we will be, so the chi-square distribution looks something like this, right? We will set up a critical value, as always, right? And that we want to have, for example, at 0.05, right? There's going to be a critical value here, that from that you will be on the null hypothesis, remember? And from to the right, you will be on the alternative hypothesis. So if your value is less than the critical value, you cannot say that the distributions are different. If you are on the right of the critical value, you can actually say they are statistically different. Okay? So this value, we have to find the critical value C. And the way that you do it is, for the chi-square distribution, you need the probability, the significant level, and the degree of freedom. The degree of freedom for a chi-square distribution is, as always, it should be the number of points minus the parameters. In this case, the number of points is actually the number of bins that you have, the number of classes that you have created, minus 1, because you are, there's one parameter that you are estimating here, which is the critical value. So you will have 5 degree of freedom. So you go to your table with degree of freedom 5, and we want to be sure at the 5% level, so our alpha is 0.05. So you go with 95%, and it's 5 degree of freedom, and your critical value, if you go to the table, give you 11.07. So since 11.07 is less than our statistics here, then we cannot say that these distributions are different. Even they look quite different, statistically you cannot say that it's different from a uniform distribution. At least you don't have enough data or enough evidence to say that. So in theory you can say that this die is honest. Alright? So that's how you use the chi-square in this case. Another example, which is a little more complex, let's say that we have measured resistors, right? We know the resistor has tolerance, and we want to know if the distribution of our measurement follow a normal distribution in this case, not a uniform, but a normal distribution, okay? Then we have collected some resistors. We have collected 5 that have 48.5 ohm, 11 that have 49.5, 35 that have 50.5, and so on and so forth. We have collected in total 1, 2, 3, 4, 5, 6, again 6 resistors there. And we want to know if this follows a normal distribution and with some mean and variance that we don't know. So again, we can separate this in 6 classes, right? So in this case, the normal distribution is something like that, and we hope that our classes will be more like this. So the difference between the classes and the theoretical distribution is not too large. So how we do this? How we define the means now? Well, we will have to do something like this first and like this, because to the left and to the right we don't have measurements. So we will assume that this will finish at 49, and this will start in minus infinity. Okay? And this will finish here in 53, and this go to infinite on the right. Then you will have 49, 50, 51, and 52. So one class will be from minus infinite to 49, the second class will go from 49 to 50, the third class from 50 to 51, so on and so forth. That is the way that we define our classes, which are 6. And now for each classes, we have to estimate the theoretical distribution for that particular. And we use our phi function for that, right? The normal function. How to know the particular normal distribution that we use in this case, we have to estimate the mean and the variance of the distribution. The only way that you can estimate that is using your data, right? So basically, you calculate the average of your data, which give you around 51.05 ohms, and you calculate your variance or the standard deviation from your data. With these 2 points now, you have the formula to use to calculate the theoretical distribution at the different beams that we have done. Okay? So, how do you do that? This is a much beautiful way of representing the classic here that I did before, but it's the same. So the first class is here. How do you do that? This is the normal distribution. You have to calculate this area, right? such that it's less than 49, right? From minus infinity to 49. So you have to place your 49 as a part, right? This is your mean and this is your standard deviation that we already have calculated. And then if you do the math, it gives you this value. This value you could enter the table, but you know that 1 minus the positive of this value, because it's mirror symmetric, will be give you the same value. So since the tabulation is for this value, we do 1 minus the phi, right? And if you do, then the area that is less than 49 is 0.044. So this is the first value that you get. The second is an interval, which is in the mean. Remember that we are trying to do this. I always try to keep you focused here. We will try to do this, right? So we cover these intervals. Now we go to the second interval, between 49 and 50, okay? And then you value your phi function in 49 and 50. Again, you enter the table, and it gives you some value here. So that's for that. And you repeat that for 50, for 51, for 52, for 53. And these are the values for that. Okay? And the last one is easy to calculate because this last part will be 1 minus the rest of that. Right? So the last port that is larger than 53, or between infinite and 53, it will be just 1 minus all the one that you have calculated. So with all that information, now you can build your table. The first row of the table is going to be your values of it's your data, basically, right? It's each of these values for each of the classes. Here you have. The second part is the number of points that you have, the frequency that you have collected this value. We already saw. The third column is what you have calculated here. All of these theoretical probabilities, right? Here. And then it's just multiplying. In this case, we have in total 100 collection of data, and we will divide it for the theoretical part. We will divide it exactly by 10 segments. Okay, so you just multiply multiplying your probability by the n. I give you just moving basically the column on the left. Then you make the difference between this guy and this guy, and you fill the fifth column, and if this difference, you square it here, and you divide it by the theoretical area, you get for each point a value that if you sum it together, you get your chi-square statistics. And again, with this chi-square statistic, you will go to the table, and you will compare with the, depending on your alpha you get. So our chi-square statistic was this one. Now we want to be very sure, so we want to be an error of 0.01. So in the table, you will go for the critical value with 99%, right? And the degree of freedom here would be the number of classes that you have, minus 1, because we lose 1 degree of freedom by estimating the number of classes, because we do it arbitrarily. Minus 2, because we estimate in the mean and the values. So you lose another 2 parameters. So the degree of freedom here will be 6, minus 1 is 5, minus 2 is 3. This is your degree of freedom. So with 99 and 3, you go to your table of the chi-square, and you find your critical value, which is, just to refresh you, critical value, in this case at 0.01. To the right, you reject the null hypothesis. To the left, you accept the null hypothesis. 11.35 is larger than our chi-square, so we are again in the null hypothesis, so we can not say that the distribution that we have is different from a normal distribution, or at least we don't have the evidence to say that. All right? So that's the way you calculate. In this way, you could actually test with chi-square if your data follow normal distribution before you enter to another test. Okay, I'm not sure if you are fully following me, but I hope at least you have the idea of what we are doing. We just created a distribution and compare it to a theoretical one. And we want to compare it statistically, and we want to be sure by some critical value. So let's say that we now know that it's the normal distribution, so then we can actually continue and say, okay, we're gonna compare two samples, two means, and we want to use some tests for that. And one test for that is the t-test, which follows a t-distribution. The t-distribution was defined by William Gossett. And there is one reason why William Gossett is the distribution is not called Gossett distribution. And the reason is because he was working for Guinness. Okay? So this guy was working for Guinness, and he was testing the taste or how much people like Guinness. Okay? The problem with testing beer is that you cannot give it a lot of beer to the people, because at some point they will say anything, right? So you have to be careful with how many data you have, right? The problem is that if you have, he noticed that if you have not too many data points, then your distribution that you assume that is normal, it becomes a little bit less normal, or in a little lower values. And then he said, if we just have variable x that follow a normal distribution, and we divide it by another variable that follow a chi-square distribution, that gives you a new distribution that follow better the data he was using. Okay, and he called this the student t-distribution. And he called it that because if he would call it Gossett distribution, the guys from Guinness would know that he was developing this. They would not allow him to freely publish this without a patent, and then this would not be able to be used for all people, only from the people from Guinness. And he didn't want to do that. He wanted to get this access to all the people, and then he wrote it as a student t-distribution without his name and without any reference to Guinness or anybody. But then later people realized that was he who developed that. So the t-distribution is basically like a normal distribution, but when you have not too many data points. And it looks something like this. And this is the cumulative density function of the t-distribution. They have some properties that you don't need to know, but one thing that you have to know is that also depends on the degree of freedom. T-student distribution, because it's dividing a normal variable by a chi-square value, so it has to have the degree of freedom into account. If you have a larger amount of data, then the t-student distribution approximates the normal distribution. So as the normal distribution looks really similar, you have something like a bell shape. You can also define critical values, right? You can also, it's the same, exactly the same thing that we have been doing for the last lectures. The only thing is that different from the normal distribution is that you have to take into account the degree of freedom. Okay? So again, there is going to be a table where you will have in one row degree of freedom, and the other row you have your alpha. Okay? And then you will have to look at 95%, I don't know, 10 degree of freedom, you will get your value. In this case, 1.82. Alright? So, for what is good the t-distribution? It's good to use what is called the t-test. The t-test probably is one of the most famous ones to compare means. So, it's used for many test, the most common is to compare two means. Let's say that you have two distributions, and these two distributions have two means, and you want to know if mean 1 is different from mean 2. Okay? So one thing is that they have to be far away, and the other is that the variability doesn't have to be so large that these guys do not overlap, right? So because if they overlap, they will be in some way statistically no different, right? So they have to be apart if it's possible. So why is this the case? I don't know. You want to know if the amount of sugar in one meal is larger than the amount of sugar in the other meal, then you calculate the means, and then you can compare it statistically with the student t-test. All right? So that's one way of doing it. And in this case, and there are very specific cases of the t-test. It can be that you don't know the variance well, this is population mean. Also, you can also test not between two samples, but one sample and some theoretical mean. Okay? That is another possibility using t-test. We're not going to follow this. We're just going to go to the example of two samples. So if you compare two population mean, you may know the variance, but you assume that they are equal. Okay? You may not know the variance, but you assume that they are not equal. And also could be that they are related to each other, so that these two populations are related. For example, coming from the same person. You are testing the weight of the person before a diet and after a diet, for example. And then you can use also the t-test for coefficient regression and correlation coefficient, but we're not going to do this in this lecture. So we want to focus on comparing two means with the student test. So there are a few assumptions to use the t-test. The t-test is a parametric method, so you have to get parameters, you get the mean and the standard deviation. For that, just have a good estimation, your data has to follow a normal distribution. Okay? You can check that with the chi-square method, or you can use another method that we'll see next week. Second, they have to be independent, so they cannot come from related samples. So sample 1 has to be totally independent from sample 2. And they have to, in this case, we're using unknown variance, but they are the same. Okay? So, as always, we do, and we have been doing this for the last weeks, we set up our hypothesis testing. Okay? So, let's say that we have mean 1 and mean 2, right? And the hypothesis, the null hypothesis is that the means are equal, and the alternative hypothesis is that they are different. Okay? And that's what we're going to test. So how to test that? First, you have to choose your alpha. So how the level of confidence that you want to be, 95%, 99%, whatever you want. The second, you have to create your t statistics. And how you create this t statistics, this looks a little bit big, but it's not so complicated. First, we want to know if the mean, and this is what's called x and y, the two samples, the difference between them. That will give you an idea of how different they are, right? If this becomes 0, they are not different. If it's larger than 0, maybe they are different, right? And then the other thing is, it's not the same to have two distributions that look like this than two distributions that look like this, right? Even the means are different, the variability is so large that you cannot really say that they are different, okay? Because there are many points that share each other. So you divide that by the variance of each of these distributions, and it's a weighted sum here, and n here is the number of samples that you have, the number of points on the distribution, and in that way, you also multiply by the number of samples that you have. In that way, you create your t statistics. you would create these t statistics, and depending where the t can enter here, wherever it goes, you will reject or accept the null hypothesis, as always we do. I keep repeating this. I hope the concept of null and alternative hypothesis is clear. If not, please let me know at some point. Once you have done that, then you just can say if the means are different or not. The t-distribution will have degree of freedom. So the t-distribution is the number of samples of one distribution, the number of points of one sample, plus the number of points in the other sample, minus 2 degree of minus 2, because you are estimating the mu and the variance. So this comes from estimating the mu and the variance. Okay? In this case, we are assuming that we are creating a pool, just a pool variance, just to make this a little bit more, this formula a little more relaxed, and then you can come up with something more simple. That's all that I'm doing here. And then you do the comparison as I say. So let's go, for example, that always make it a little bit more clear, I hope. So let's say that you have two pumps, right? You have pump A and B. They pump water per minute, liters of water per minute, okay? And you want to know if these two pumps work equal, or one pump pumps more water than the other per minute, okay? So you will have two pumps, and you will collect data from these pumps, right? You will collect how much liter per minute each pump pumps in many days, okay? And this data will be X and Y. So you will have two distributions, and you will have one mean for pump A and one mean for pump B, and you also will have a variance for A and a variance for B. And let's say that you have collected data, you have collected 10 points in time for A and 12 points in time for B, and these are your mean and this is your variance, okay? And now with that data, you want to figure out if one pump is working better than the other or pumping more water than the other. What do you do? And you want to be sure or making an error at the 5% level, okay? So with that, you pretty much have all that you need. First, you set up your hypothesis. In this case, we hypothesize that the null hypothesis that the pump A or 1 is pumping less water or equal than pump 2, and the alternative is that pump 1 or pump A, sorry for the A means 1 and B means 2, and that the third pump pumps more water than the second. Okay, so it's in this case single take test. So first we have to find our critical value. In the student t-test, t-distribution, we have to find our C, okay, at 0.05. To the right, you rejected the null hypothesis. At the left, you accept the null hypothesis, okay? So, critical value, C. We need to have the degree of freedom and the confidence level. The confidence level, already we know it, is 95. Degree of freedom, number of points in one sample plus number of points in the second sample minus 2. So 10 plus 12 minus 2, 20. So we have degree of freedom, we have confidence significant level. We go to the table with that, and we get 1.725. So the critical value here is 1.725. All right? That is what we have. What is our T statistics? Well, we have to build it. We first create this pool variance. We fill N1, variance 1, N2, variance 2. We have all these values we have calculated, and these are our pool variance. We place that and we calculate our T value, our T statistics, right? It's just putting the numbers there. and our t statistic is 2.572. So, if it's true, without reading the last paragraph, if the statistic is 2.572 and our critical value was 172, what we do? We reject the null hypothesis or we accept the null hypothesis?
Reject.
Yeah, good. Well, yeah, see, at the end I have you there. Nice. So basically, we can reject the null hypothesis. So it looks like pump B delivered less than pump A, at least an error of 5%. Right? We are sure by 5%. We can make it still a mistake, but the mistake will be with low probability. Okay? Just with that data. And you can generalize this with your experiment, your data, your work, whatever you're doing, you could imagine that you could compare this. The only thing is that the distribution has to be normal, right? If not, you cannot use this method. With that, I hope it was not too much for the first lecture of the year. Thank you for being here. It's early and nobody wants to be with this weather, and I appreciate that. Yes.
The last value in the previous slide, that value.
Yes. Which one?
C value, C.
Yeah, C.
Value. That is also calculated from
The table.
Distribution table.
Exactly. This comes from the table. The T student distribution is tabulated, and then you look at the degree of freedom and you look at your confidence
This is
level.
different than chi-square table.
Yes. This is another distribution. This is the T student distribution.
For exam, we have to carry all the tables along.
No, in the exam you will have table that you need. If that is the question. So no worries, you don't need to. And your scripts, you can print out your scripts and can bring it to the exam. Okay? But nothing that you have to remember table, don't worry, and or find it on the internet, nothing like that. So no worries about that. For the ones that were not here, when I said next week I have to travel, so I'm not gonna be here. Again, it's gonna be a video, but after the next week, I will continue with in-person lecture. All right? So, thank you so much for being here, and Happy New Year, and let's say that 2023 will be a successful one. Thank you.